Hello. In this video, we will talk about using Poisson random variable to approximate a binomial random variable. So we know Poisson random variable is a discrete random variable, which means it can take values 0, 1, 2, 3, and so on within a particular time period. And within this time period, there is a constant average occurring rate called lambda. So for example, we have known that the average coming in telephones in a call center within 1 hour is 4 times. So we can think this lambda is 4. And then we can estimate or calculate the probability of next time interval that's coming the random number of telephones. So this number can be 0, 1, 2, 3, 4, 5, and so on. And average is 4, right? So the probability of calculating such random numbers with specific value for I is 0, 1, 2, 3, then be calculated as this formula. And here the lambda in this example will be 4. So I is the specific value for x. So for example, x equals 3, then we just use 3 factorial in the denominator, and in numerator will be e minus 4 times 4's 3 in power. Then we have to calculate one by one for different values. And for the binomial random variable, which is n trials, or these trials called Bernoulli trials, has a success rate. So for each trial, there's a probability of p that can be success or not success. So binomial is 2 from the Bernoulli trial, which has 2 binary results, right? So success or not success. And binomial random variable is also a discrete random variable, which means we will count how many success during n, and we are interested in the probability of this x, this success time in the n independent Bernoulli trial. So, but if n is very large and p is very small, for example, we have 10,000 times of such Bernoulli trial and the success rate is only 0.01 for each trial, then the success number probability can be calculated approximated by a Poisson random variable, and with the average lambda is np. So for example, if we have 1 hour, if we have 10,000 times trial, and each trial has 0.01 success rate. So NP is 100. So this is approximated by a Poisson random variable during a time interval with average lambda is 100. Then we can model this as a Poisson random variable, and if we want to know how many success, for example, 90 times success, then we just fill x equals 90 in a Poisson probability, with the lambda is 100. Then next we show 2 examples. And the first example is suppose the probability that an item produced by a certain machine will be defective is 0.1. And the problem is find the probability that a sample of 10 items will contain at most 1 defective term. Assume that the quality of successive items is independent. So although this example, the n is not very large, but if we think n compared with the probability, so we can see n is very large compared relatively moderately large than this probability. So we can also use approximation from Poisson random variable. But first we just use the formula of binomial to calculate the exact probability. Because we want to know the contain at most one defective item's probability. So this will contain two parts. The first part is the defective item is 0, and the second is defective item is 1. So we just use binomial probability formula. This is a combination of 10, 0, then success rate 0 in power, and not success rate is 0.9. This is 1 minus p, right? Then 10 in power. Then plus second item is for the success rate, success time is 1. So combination 10, 1 times 0.1 and with 1 in power, then times 0.9 and with 9 in power. So the probability of this binomial distribution is 0.7361. Now if we use Poisson random variable to calculate the probability of no more than one defective item, this is same as to say that we have a Poisson process with one time interval and with MP is 1, right? 10 times 0.1 is 1. So we can use also two parts. The first part is 0 factorial in the denominator, and with e minus 1, then times e c as 1, 0 in power. Second is 1 factorial in denominator, and the numerator is e minus 1 times 1 in power. So the result is about 0.7358. So very close to the exact probability when using binomial random variable. And the second example is consider experiment counting the number of alpha r particles given off in a 1 second interval by 1 gram of radioactive material. So if we know from past experience that on the average 3.2 such alpha particles are given off, so what is a good approximation to the probability that no more than 2 alpha particles will appear? So because we want to note large numbers, process, and how many, so this is a binomial Bernoulli process and can be modeled with binomial random variable. But we can also use Poisson random variable because the process is very large and success rate is very low. So we can think of this is a Poisson process, Poisson with the random variable with the lambda is 3.2. Then the probability of no more than 2 can be calculated with 3 parts. So this is the first part with 0 defective, 0 given off. And this is second part with 1 given off. And this is third part with 2 given off. So the total probability is about 0.382. Thanks for watching.